Okay, I am recording. So like I said, what we're going to be doing today is going through review questions for exam 2, but that doesn't mean you shouldn't bring up questions of your own. Okay, I've tried to encourage you throughout the semester that if you're having questions about the homework assignments, just ask me those as you go along. Each homework assignment has a message instructor link in it, and you can send email so I can see the numbers you're working the problem with. But if you still have questions about it, this would be a good time to bring it up. What I'm going to do is kind of go through like every flavor of problem that we kind of covered since our last exam. And that's primarily on taking derivatives and using the derivative and the second derivative to tell you things about the function. As I've mentioned too in class, we're not going to actually graph a function by hand. I mean, there's no point in doing that in the real world. The point of knowing how to do that is so that you understand the information that a derivative and a second derivative tells you about a function. And in case you're wondering, in business, like who cares? Why do we do this? You might have only been exposed to, say, basic arithmetic operations, say in accounting or something like that. But financial models are have a lot more power to them because they're expressed as mathematical equations. So if you're going to wind up doing anything with finance, even if you're not the person developing these equations, you're probably going to use software that uses equations and calculus to do things like price options or things like that. Okay, so just understand you might not see the math, but it's in there and it's usually in software. Okay, so that said, let me get started. And again, please feel free at any time to unmute yourself, ask a question. I know it's kind of cumbersome to type everything in the chat, so don't hesitate to unmute. I'm going to start out by sharing my browser. And I'm going to show you, again, where we are in the course. We're currently in week 8, which means we're about halfway through, folks. Okay, we've got 15 teaching weeks, 15 instruction weeks this semester, and a final exam week. Okay, it's like a week shorter because of spring break, which is next week. So here is what we've got going on in week 8. Okay, I'm going to be using this file, practice for exam 2. Okay, and it's just got a bunch of questions that's related to the material since exam 1. And it has a solution key with it. Okay, but it doesn't show you how any of the problems are worked out. So what I'm going to try to do is in this class session, I'll go through about half, hopefully a little bit more than half of these problems. And then when we meet again on Thursday, we'll go through the rest of the problems in the review. You can see as far as assignments, there's no new material this week. All of what you're going to be doing is reviewing for the exam. Here's exam 2 right here. You get 1 attempt on it. Okay, so make sure you've got all your materials together when you're ready to take the exam. And yes, use whatever materials you need from the course. Use the calculators that I've showed you. If you don't have a TI-84, have all that stuff like open in tabs ready to go. And then again, as you're working on the exam, okay, write down as much work as you can for each problem, right? And then at the end, once you've submitted your exam, you can, there are apps that will let you take photos with your phone and then collect the photos into a PDF, like right on your phone. And then you can upload that here. Okay, if you have a scanner, go for it, scan in your work. Okay, but give me something so that I can award you partial credit, because you probably figured out by now that trying to do homework and exams online, when you're being graded by a computer, there's no room for, well, I was almost right. There's none of that. So that's why I'm going to go over your exam with your work, and I'm going to give every, if you can, I'll give you partial credit. So don't be worried about the grade on the exam when you finish. Okay, that's not your final exam grade, just like we did for exam 1. 1, okay? So before I move on to actually reviewing, let me ask any questions about the exam. Any questions about the exam? Anybody have any concerns or whatever? No? Okay. Okay, not seeing any. And again, you're always, how many questions do we have? Okay, it's pretty, again, I don't honestly remember. So let me see if I can open, I can't open this one right now because I'll screw things up. I would say there's probably about 20 questions if I remember correctly. I know in the review we have about 24. And let me see if I open this, I think it will tell me the time frame if I can look at it. Okay. Okay, so here's basically the information. Okay, you've got 1 hour and 40 minutes. Okay, and then prepare to finish it as if you were in class, like an hour and 40 minutes. Okay, and the exam closes after that. Okay, so show your work. Okay, scan it in, or like I said, use an app that will take photos from your phone and create a PDF with it. There's free apps for that. Ask me if you're having trouble finding those. Okay, and basically you can use all of the material in the course. Okay, here's one app called Adobe Scan. Okay, and again, remember, whatever grade you get on the exam is not your final grade. I can go through your work and try to award you partial credit. Okay, so again, probably about 20-ish questions. Okay, and again, the questions that we're doing on the review, all of the questions aren't super involved like that, but you should be comfortable doing those type of questions. Okay, but the important thing is use the resources that are provided. Use Desmos, use the web online calculator, use your TI-84. Okay, and again, it's not very efficient to have to like go back through the course material, but there is nothing that's going to prevent you from doing that. There's no special lockdown browser or anything like that. Okay. In my experience, putting those things as constraints on students just makes everybody get a little anxious. So what's the point? Use the materials you have. Just do the exam yourself. Okay. No help from your sister or, tutor or anything like that. Okay, did I answer your questions? Did I answer your questions? Anybody, any other questions? Okay, so again, feel free to ask more questions as we're going through this review, okay? Because again, you can watch me do it lots of times, but until you do it and have a question about it, it really doesn't stick. Math, unfortunately, is a participation sport. Okay, the questions are going to be similar to the homework and similar to the ones that are in this review. So yes. Okay. The important thing is you want to conceptually understand what we're learning about the derivative. Please don't just think of it as plugging things into formulas and cranking. There are a few questions like that, okay? I'll be honest. But most of it is, so if a derivative is positive, it means the function's increasing. If a derivative is negative, the first derivative, it means the function's decreasing. Your second derivative tells you about concavity, right? Second derivative negative, concave down. Second derivative positive, concave up. And if you can handle all of that along with the graph of the function, you're good. Okay, you're good. Okay, that's really what you need to understand, are those basic concepts. Okay, so understand the broad basic concepts. Okay, and then the rest of it, leverage it off onto technology. Okay, I've told a number of you there are calculators out there that will factor a polynomial if it's factorable. Okay, you can use it. Okay, there are calculators out there that will do the quadratic formula for you. You can use them, okay? Again, this is not meant to be a test of how well you can do calculations with a pencil or how much algebra you remember, although you need to know some algebra to get this to work, okay? But I'm telling you to leverage as much stuff off onto, technology as you can, all right? And what's more important is understanding what information you're getting about your function from calculus, okay? Is that clear? That's what we're going for. Yeah? Okay. Thank you. All right, I appreciate the feedback, folks. All right, so while, give me a minute and I'll open up this practice 2 exam on my tablet and share it with you. Again, feel free to open it in a tab or, print it off if you have that capability. All right, let me share this. Okay, so everybody should be seeing practice test 2. And again, the first bunch of questions are all about finding the derivative, okay? And basically what you need to be able to do in order to do this is figure out which derivative rule to use, okay? In the one of the previous modules where we started introducing, say, the power rule, the product rule, the quotient rule, I put a sheet in there saying derivative rules and examples. Okay, so you may want to go back a week or two and look for that sheet. Okay, and it's got everything summarized. Okay, although to be honest, one of the things I think is really useful if you're studying for an exam is to make your own cheat sheet of what you think's important. For example, put in the power rule, the product rule, the quotient rule, the chain rule. Those are the main rules we used. Okay, what's the basic pattern for differentiating a log, an exponential? Okay, because they're different from polynomials. And then what does the second derivative tell you? What does the first derivative tell you? You could probably fit that all on one side of an 8.5 by 11-inch sheet of paper. Okay, and that's what you need in order to get through these problems. So let's talk about them. Okay, this first function is a polynomial. So all I'm going to use on it is the power rule. And again, if you've been keeping up with the homework, you've had an opportunity to practice this by now. That's another good reason for at least, getting the homework started in the week that it's due, is so that you're up to date with the practice on what it is we've covered. Okay, if you try to leave it all for right before the exam, first of all, you're going to run out of late passes, and secondly, it's way too much to understand in one lump. Okay, so the power rule says if I want to find y prime, okay, pull away the coefficient, bring down the exponent, drop the exponent by 1. Okay, and power rule is what you use when you differentiate a polynomial. Do it again, pull away the coefficient, bring down the exponent, drop the exponent by 1. And again, I'm showing every last step. If you're doing this yourself and you've figured out how to combine the steps together or do it in your head, that's fine. All right, the last term is a constant. That gives me no term in the derivative because constants don't change. And the derivative is telling me the rate of change of y. So a little bit of algebraic simplification gives me 15x squared. And all of this over here, you might remember x to the 0 is simply a 1. So this is 2 times 1 times 1, or just 2. Okay, so pretty much that's that one. Okay, now if I look at function number 2, okay, what you should see is a composition okay? And it's a composition of a cubic inside a cubic. Okay? The outer function is this thing cubed, okay? So you can think of it as like u cubed, okay? And what's the inner function? It's this cubic here, 5x cubed minus 2x plus 1. So this requires the chain rule. Okay, and again, you need to recognize that before you even start. Okay, so a big part of doing this is recognizing the shape of the function you're looking at. So the way you differentiate a composition is you differentiate this outer function, okay, which is this thing that you could call u cubed, okay, and you differentiate that by bringing down the exponent, leaving this alone, and dropping the exponent by 1. Okay, this is the derivative of the outer function. Okay, and then the other part of the chain rule says multiply that by the derivative of the inner function. Okay, and yes, you do need parentheses. Okay, because you want to multiply this by all of the terms in the derivative of the inner function. So again, I'm going to speed it up a little. Okay, I'm going to have the 5 out there and then multiply it by the exponent. Okay, so 5 times 3x squared minus 2 times 1x 0. Okay. And again, if you simplify it up a little with algebra, okay, you're going to get 15x squared. And again, it's perfectly okay to leave it like that, okay? If you wanted to go a little bit more nuts, you could multiply the 3 and this, okay? But it's okay to leave it like this. It should be okay to leave it like this. In other words, if you show me this in your work, you're going to get full credit. Okay? Everybody all right with that one? Anybody questions about the chain rule? Numbers for the exam, do you want us to determine? You don't have to tell me that, okay? You don't have to say it, just show it in your work. Okay, so basically just show it. I'll recognize it as the chain rule. Okay, so show me, like, even if you just show this, okay, that's fine. I understand what you're doing. Okay, you can see there's not a ton of work to show for a lot of these. Okay, now number 3 requires that you know something about rules of exponents. Okay, because otherwise you can't even get off the starting line with this problem. So the first thing you want to do is rewrite the roots with exponents. Okay, and again, why are we going to do that? So I can use the power rule. Okay. That's the object of the game. Okay, if I can rewrite it with exponents, I can use the power rule. Okay, so I'm just going to do that. Notice I haven't done any derivatives yet. This is x to the 1/2 plus. Now, take a look at this thing here. Okay, I'm raising x to the 4th. Okay, so that's a power. And I'm taking a cube root. Okay, so down here in the denominator, x has an exponent of 4/3. Okay, the 4 in the numerator is the power. The 3 in the denominator is the root. Okay, and now because it's in the denominator, if I bring it up here, it's going to be negative 4/3. Okay? Does everybody understand why the exponent is negative 4/3? Understand why the exponent's negative 4/3? Okay, again, this is important. If you can't do this step, you can't take the derivative. Okay, so again, exponents here in the numerator, okay, powers rather in the numerator, roots in the denominator, and then if this whole expression is in the denominator of a fraction, it has a negative exponent. Okay, so now once I'm able to do that, I can just use the power rule on each term. Okay, bring down the exponent, drop the exponent by 1. So 1/2 becomes negative 1/2, right? Start with a positive 1/2, take away 1 whole. Now you're on the negative side of 0. Okay? Plus negative 4/3, bring down your exponent, and then drop the exponent by 1. Okay, so negative 4/3 minus another 3/3, negative 7/3. Again, if you're fighting with your negative exponents or your fractional exponents, use a calculator to help you, okay? The Web 2.0 calculator that I have in the course, let me just show you how that works. Okay, suppose I have negative 4/3, and I want to subtract 1 from it. Okay? Notice, yes, it gives you a decimal here, which isn't helpful, but see up here, there's negative 7/3. Okay? So it will do the fractional arithmetic for you. Of course, on a TI-84, you would use MAT213. Okay? So again, I'm just going to share my TI with you, for those of you who have a TI. All right, and turn it on. So on the TI, you can either use alpha y equals, okay, and make it negative 7/3 minus 1, and it will do the math fracking for you, okay, negative 10/3. That's not, I did it the wrong way, sorry. I meant it to be negative 4/3 to start with. Okay, so let's do that again. Negative 4/3 minus 1, negative 7/3. Okay, if you don't like the fraction template, negative 4 divided by 3 minus 1, decimal, then math frac. Okay, either way, you can do this on your calculator. Don't fight with this, doing it in your head if you're not comfortable. Okay, use the technology. Okay. All right, so then there's just a matter of simplifying things a little. And again, it's not a whole lot of simplifying. If you take a look at this first term, you can see that x has an exponent of negative 1/2. That's going to put it in the denominator with the 2 and put it under a square root sign. Okay, 1/2 means square root, negative 1/2 means the square root's in the denominator. Okay. Now let's take a look at this coefficient. I have a plus, a negative. Okay, so I'm just going to say minus. The 4 goes on top, the 3 goes on the bottom. Okay, so plus a negative number is the same as subtracting. Okay, this is also a negative exponent, so it's going to go down in the denominator. But you can see it's a cube root of something raised to the 7th. Okay, so that's what that simplifies to. Okay, again, it depends on how the problem is worded as to whether it's going to accept it like this or whether it wants you to write it with roots. Okay, so do your best. And like I said, if you get it to this point, I'm going to give you like absolutely most of the credit because you did the calculus part right. Okay, that said, you should be able to go to the next step. okay, because this was stuff from a previous class. But again, I'm more interested in your ability to do the calculus part. Okay. Any questions on that one? Okay. Number 4. Okay, I'm going to also rewrite this because again, I have a root. Okay, and I'm going to rewrite the root as a 1/3 power. Okay, so you can see that in calculus, algebra is used as a tool to simplify before you get started with doing calculus and also afterwards. Okay, the main reason for simplifying afterwards, I mean, these are just textbook problems, so there's no reason to simplify them. But if I were actually using them to tell me something about my function, I would want to get them as simple as I could get them so they're easy to manipulate. Okay. And you'll see that in the later problems. Okay, so here I've rewritten my cube root as the 1/3 power. And now you can see this is a composition of a quadratic inside a cube root. Okay, because again, the 1/3 power means I have a cube root. So I need the chain rule here. Okay, so again, the way the chain rule works is you take the derivative of the outside thing first, and that's like u to the 1/3. So I'm going to bring down my exponent, leave the thing in parentheses alone, and then subtract 1/2 from 1/3. That gives me -2/3. That's my outer function. And then if I want to take the derivative of the inner function, I'm just taking the derivative of x squared, because the 7 won't give me anything. That's just 2x. Okay? And again, there could be lots and lots of simplifying here. Okay, if you want to simplify it, that's the calculus step. Okay, that's the must-do step. Okay, so take a look at what I have. I have a 1/3, so I know I'm going to have a fraction like this. The 2x is in the numerator. Okay, and this quantity in parentheses is in the denominator. Okay, because it has a negative exponent. I'm taking the cube root of it, and the quantity in parentheses is squared. Okay, if you want, you can leave it to the 2/3 power. Okay, and again, it's convention to not put the 1 there. Okay, so there it is, totally simplified. But again, going from here to here is just algebra. This is the calculus step. Okay, everybody okay with that one? Again, I'm trying to pause between each problem in case folks have questions. Okay, so please, let me know if you have a question. Okay. So if I take a look at number 5, okay, what is the shape of number 5? I'm asking you a question of number 5's f of x. Okay, what is the shape of number 5's f of x? What have you got here? Okay, feel free, just answer or put it in the chat. What do you see here? Anybody have any ideas? So what I'm asking you is, if you were to do this problem, what is the overall shape of the function? How would you start? Is it a quotient? Is it a composition? Is it a product? What is it? Okay, you're looking at just the root part. The root part is a composition, but what about the whole thing? What about the whole thing, including the 2x? Yes, you're right. This part's a composition, but what's this? Yeah, it's a product. Okay, so this is a product which contains a composition. Okay, so it's worthwhile stopping and thinking about what it is you've got before you just start doing stuff. Okay, you're mentally trying to make a match between all the rules you have and what this looks like. Okay, so I'm seeing, first of all, a product. There's a multiply between the 2x and the root. Okay, so again, I like to call my functions u and v. Okay, and again, you may call them f and g. Again, since the function itself is called f, I don't want to do that. So here's the way the product rule looks. And I'll write it right here. Okay, then f prime of x is u prime v plus u v prime. Okay, and again, get in the habit of just writing it down, okay? Because then all you have to do is find u, v, u prime, v prime, and plug it in, and you're good, okay? Don't spend a lot of time, searching for it. Just write it down right there. And then I can say, all right, well, my u function is 2x, and my v function is, I'm going to rewrite it as x squared plus 1 to the 1/2. Again, I'm rewriting my square root as a 1/2 power. And I'm doing that in preparation for handling the composition, which means I need the chain rule. Okay, so this is like chain rule inside of a product rule. Okay, that's important to realize. Okay, then I'm going to take the derivative of u, that's just a 2. The derivative of v is going to require the chain rule. Okay, so first I'm going to, this is a quadratic inside of a square root. So I'm going to handle the square root first, the outer function, bring down the exponent, leave the inner function alone, and then subtract 1 from my exponent. Okay, here's my outer. And then I just differentiate the inner function. Okay. If I want to make it look a little bit more, easy to manipulate. Okay, I've got 1/2. That tells me I've got a fraction. Okay, the 2x is in the numerator because there's no negative exponent on x. And this expression is in the denominator and it's a square root. So this looks like this. Okay, and again, you might say, hey, guess what? The 2's cancel out, which is true. All right, so there's my v prime. And then it's just a matter of plugging it in to the pattern in the rule. Okay, so u prime times v plus u times v prime. Okay. And again, depending on how much manipulating you want to do, okay, you can do this. Okay. And again, I wouldn't go nuts, okay? In the worksheet that I gave you, what they did next was they rationalized the denominators and don't. Just stop. Okay, right here. You can stop here. Okay, the important thing to realize is you did a chain rule here, and that showed up as part of the product rule here. Okay, so again, this is, I have no idea what that is, folks. Sorry. Okay, u prime v, u v prime. Okay, just so you can see the pieces. Okay, so let me stop and ask, okay, with the product rule and the chain rule inside of it. Okay, I'm stopping and asking for feedback. Are you okay with this? All right, so far? I strongly urge you, write this stuff down whenever you use the product rule. Write out the product rule and then write, here's u prime, here's v prime. And then it's real easy to just plug in the bits. Okay, don't try to do this stuff in your head. Okay, write it all down. And then you've got all the pieces. Okay. Now, again, if I look at number 6, okay, I'm seeing a quotient, and I'm noticing it's got 2 terms in the denominator, so I'm thinking quotient rule. Okay, it is possible also, if you were thinking of doing it, to rewrite it as x times 1 minus x squared to the negative 1, and then you would have a product rule with a chain rule inside, just like this one. There's more than one way to do these, okay? But I'll show you with the quotient rule. Now here's how the quotient rule works. Sorry. So if my function is a quotient of u over v, then the derivative of it will look like this. Okay, now because this is going to have a subtraction in the numerator, it's important to realize it leads with the function that's in the denominator. Okay, so whenever you're writing it, regardless of what you call your functions, okay, the first thing is the denominator function times the derivative of the numerator function. It has to be in that order. Unlike the product rule, where the order you do the individual products in doesn't really matter. It's just one function times the derivative of the other. Here, because of this minus sign, okay, they have to be in a particular order. Okay, so there's my quotient rule. And again, I would get that right off a cheat sheet. And then I have, again, my functions. U is the x in the numerator. V is the 1 minus x squared in the denominator. U prime is 1. Okay, and v prime, okay, the 1 doesn't give me anything, okay, but again, I can't lose this negative 1 coefficient in front of the x squared. So when I bring down the 2, it's going to multiply by the negative 1, so negative 2x. Okay, so here the 1 gave me a 0, and I'm still left with a negative sign in front of x squared. I can't ignore that. Okay, and then it's just a matter of filling it in the quotient rule. So I have v first times u prime, and that's just times 1. Okay, I'll put it there so you can see it, but it's not necessary. Okay, and then it's u times v prime, which is negative 2x. Okay, and then the whole thing is over v squared. Okay, and again, you can do some cleanup algebraically in the numerator, okay, because you're going to have 1 minus x squared, And then you notice here you've got a minus x times a negative 2x. That's going to be a plus x squared, plus 2x squared. Okay, and then you can see one of these cancels out. I've got a negative x squared, a plus 2x squared. So this becomes 1 plus x squared over 1 minus x squared. Again, if you want to do all the simplifying. Okay, so again, this is just the quotient rule. And this didn't have anything else hidden inside. Okay, with the quotient rule. Questions about it? Okay. Now in this example, because I had two terms in my denominator, there was no real way for me to simplify it unless I wanted to rewrite it as a product of x times 1 minus x squared to the negative 1. I don't know that that would have been any easier. But let's take a look at question 7. And I want to ask you, okay, for question 7, how would you start it? And in particular, think if there's more than one way you could start it. Is there more than one way? Take a minute, look at 7, and then put your answer in the chat or unmute and let me know. How would you start it? Anybody have any ideas? Okay, but what rule are you using? What process are you going to use? Okay, I'm asking you to back up a minute. Okay, so me is thinking it's a quotient, and you could certainly use a quotient rule. Absolutely. Is there a potentially simpler way? Okay, I saw something there. Jesse, let me back up and see. Convert 2 to the x squared. Okay, you could do them. Jesse saying I can bring the 2x to the minus 2 upstairs, but be careful. You would have to bring it up like this. Okay, not power product. Okay. All right, so everybody's thinking different ways, and all of your ways are valid. Okay, there's at least 3 ways to do this problem. 1, use quotient rule. Let me use A, use quotient rule. Okay, rewrite as a product. Okay, but there's a simpler way. Divide 2x squared out of each term. There's only one term in the denominator, right? But that's saying divide out everything in the numerator by 2x squared. So let me show you what I'm saying. Okay, all of these are valid ways. Okay, and if you choose any one of them, you'll do fine. Okay, but I'm just trying to point out what's the easiest way to do it. Okay, so here's what I'm saying. Take each term in your numerator and divide it by 2x squared. Okay, because that's what that's telling you. Okay, take each term and divide it by 2x squared. And then I can use rules of exponents to simplify it, okay? So again, here you can see 4 divided by 2 is 2. X to the fourth divided by x squared, okay? 4 minus 2, x squared. That's that first term's quotient, right? You remember the quotient rule for exponents? Take the exponent in the numerator, subtract the exponent in the denominator. Okay, the next one has kind of a messy coefficient, but guess what? X squared divided by x squared is 1, so x disappears there. When I differentiate this, I'm going to get, 0. Not a problem. Okay, and then the last term, okay, 8 divided by 2 is a 4. And the x squared in the denominator, I'll write it as minus 2. That looks a lot simpler to me, okay? And if I were going to differentiate this, I would want to do that. And now I can use the power rule. Okay, everybody understand the algebra? Again, I haven't done any calculus yet. Understand the algebra? Okay. Yes. I'll give you a minute to look at it. Okay. All right. Now we can do calculus on it. And this is just power rule. Bring out the coefficient, bring down the exponent, drop the exponent by 1. This thing in the middle of the 5 halves is a constant, so it gives me nothing. Okay. Then I'm going to pull away my coefficient, bring down my exponent, drop my exponent by 1. Okay. And then the rest is algebra. That's going to give me 4x minus 8 times x to the minus 3, which is 4x minus 8 over x. That certainly looks like a lot simpler. Okay. And if you had taken any of these other approaches, you would have come out with something that was algebraically equivalent to this. In other words, had we simplified it enough, we'd get the same answer. Okay, so okay with number 7. Okay, it's my goal today to get at least through 12. Okay, but I don't want to overwhelm you. I've discovered from doing these reviews that students can handle maybe about an hour of this before it's like, your eyeballs are floating. So again, don't want to overwhelm anybody. Same answer for every way. They will be equivalent. They will be equivalent. So they may not look the same, but you could manipulate them algebraically to become the same. Okay. Yeah, again, the point is do it the easiest way you can. All right, so that works because one term here in the denominator. Okay, and I'm able, if I had an exponential in the numerator, I'd be stuck with the quotient rule because they're two different families of functions. This only works because I've got a polynomial divided by a polynomial, okay, and I've got one term in my denominator. So that means I can separate the numerator like this, divide each term in the numerator by the denominator. If I had a different type of function in the numerator, I'd be stuck using the quotient rule or the rewrite as a product, okay? It only happens to work in this situation. Okay, so let's take a look at other types of functions. Okay, so if you look at 8, what do you see going on in number 8? Okay, so what do you see going on in number 8? Tell me what you're looking at. Anybody have any ideas? Okay, definitely an exponential. Okay, anything else? So what's the base of the exponential? What's the base? Yep. Okay, base 4. What about the exponent? Is it just... What about the exponent? Yeah. Okay, so it's a linear expression in x. Sorry, x. Okay, so what you've got here is actually a composition of a linear, that's the exponent, inside an exponential. Okay, so that's what you've got. Okay, and again, the reason it's a composition is because this isn't just plain old x, it's something x, right? It's a number times x. Okay, the same deal would be if you had an x squared up here in your exponent. Okay, so think of it as, well, it's a function in x, like, right? It's not just x by itself. Because if I take the derivative of x, I get a 1, it doesn't change anything. If I take the derivative of this, I'm not just going to get a 1. I'm going to get that 0.01. Okay? So it's important to realize that this is a little bit more complicated. So the way you would take its derivative is you first take the derivative of the outer exponential. Okay, and the way you do that is you take ln of the base. Okay, and then you rewrite the exponential part. Right? So that's the way you do the derivative of the base A exponential, right? If this was a base E, I wouldn't have the ln stuff because ln of E is 1. Remember all that? Okay. So this is the way you take the derivative of the exponential part. But then because you've got the linear up there in the exponent, you have to take the derivative of that. So the derivative of 0.01x is 0.01. Okay? So there's the outer exponential. Okay, and there's not a whole lot you're going to do with this. Okay, if you want to rewrite it, you can put the number first, and then you could put the log. Okay, 0.01 and ln4 are just numbers, but unfortunately you can't combine them. Don't approximate the ln with your calculator. Leave it as ln. It's an irrational number, and if you leave it as ln, you're getting all the decimal places that come with ln4. Okay, if you approximate it, you're introducing a rounding error. Okay, so leave it alone, and then you've got the exponential 4 to the 0.01. Right, so this is about as simple as I can get it. Okay. Anybody questions on that one? Questions on number 8? Okay. All right, so then let's look at number 9. What do you see? Look at number 9. What do you see? Again, tell me what shape you're seeing. Is it a product? Is it a quotient? Is it a composition? Is it something else? Okay, we've got one vote for composition. Anybody else? Okay, two for composition. Oh, exponential. Okay, yes, exponential is definitely part of it. Okay. Any other ideas? Okay. What does that look like up in the exponent? What kind of expression is that? You're on the right track, guys. Just push it a little further down the track. Okay, we're looking at number 9. We see part of it's exponential, but I'm asking about the exponent. What kind of an expression is this up in the exponent? Yeah, absolutely. Okay, good for you. Okay, Nia's basically saying, oh, wait, I put all the pieces together. It's a composition of a polynomial, a quadratic, inside an exponent. Excellent. That's exactly what it is. Okay, so it's a composition. And again, all of you provided pieces to that. So that was a group effort. Composition of a quadratic inside a base E exponential. So because it's a composition, again, I'm using the chain rule. Okay, this was an opposite, chain rule. And I'm going to use the chain rule again. Okay, so the first thing I'm going to do when I differentiate this is I'm going to take the derivative of the outer function, which you could think of, well, that would be ln of e, right? I'm going to just write it even though it's dopey. Ln of e to the 5 minus x squared. Okay, here's the outer exponential. Okay, and then multiply that by taking the derivative of the inner quadratic. Okay, the 5 that's up in the exponent gives me nothing. Okay, and the negative x squared will give me negative 2x. And again, the only reason I put ln of e down here was to show you that it follows the same pattern. Ln of the base, repeat the exponential. Okay, and then you have to worry about whether or not there's anything composed inside of that. Okay, so to simplify this, ln of e is 1. Okay, because it's an ln of e is asking you what's the exponent on e that would give me e. And the answer is, well, e to the first is e, so it's 1. Okay, so I don't need it. Okay, 1 times e to the 5x squared is e to the 5x squared. Okay, so that becomes a 1. Okay, and this is just going to simplify to minus 2x. It's convention to put this variable term before the exponential term. Okay, here's your answer. Okay, anybody questions about 9? Okay. Okay, how about 10? Okay, so look at number 10. And again, I'm doing these with, I'm asking you to look at them and tell me what you see, because these are more complicated and it's important to understand what you're looking at. Take a look at number 10. What do you see? Same idea. Okay, a composition. All right. Anybody else have any ideas? What are you looking at? Okay. Well, I'm sure everybody's seeing ln, which is a log base e, right? But notice the quadratic that's the argument to it. So this is a composition of a quadratic inside log base e, or ln. So base e log. Right? So the outer function's the log, the inner function is the quadratic. So I need to use, again, the chain rule, because I have a composition. So let's do the outer first. Now, to take the derivative of a log, okay, it's pretty much, you would have 1 over ln of the base times the argument. So you'd have this, ln e, okay, and then you'd have the argument down here. Okay, so here's the outer log. Okay, and then you have to take the derivative of the argument. Okay, so this is going to be the inner. Okay, so that would be 3 times 2t minus 4. Okay. All right, everybody good with that? So the first part's just the pattern for the derivative of a log. It's 1 over ln of the base of the log times the argument. It's very similar to exponential, except inverted. Why is that? Logs and exponentials are inverses. Okay, so that's why it looks like this. And then the rest is simplifying. Again, if you look at this, you'll see log e, that's just a 1. So I'm not going to need that. So what have I got? On the top, I've got the quadratic's derivative, which is 6t minus 4. And on the bottom, I just have the argument to log. Okay? And again, I wouldn't waste my time trying to see if I've got a common factor or anything like that. Okay? Anybody got questions on the log one? Okay, I know from experience, most folks are not happy with log and exponential derivatives, so you're okay with these. All right, we're just going to do 2 more. We'll do 11 and 12. Okay, so let's take a look at 11. Look at number 11. What is its basic structure? Look at number 11. What are you seeing? Anybody have any ideas about the shape of 11? Okay, we're seeing a product. Okay. Anybody have any other thoughts? Okay. Seeing a product of an exponential and a cubic, yes. Okay, so good for you. You're all seeing a product. That's wonderful. Okay, so product. And the e to the 2x will actually involve a composition, right? It's a linear inside of an exponential. Okay, so whenever you're looking at an exponential function and that exponent isn't or isn't x all by itself, you've got a composition. Okay, so it's a product of a composition and cube. Okay, so I basically have the product rule as my overall structure. Okay, I've got to deal with the product. But one of those factors in that product is a composition, a linear inside of an exponential. Okay, so first I've got my product rule. If f of x is u times v, f prime of x equals u prime v plus u v prime. Just write the product rule down. Okay, and then that way I have it. And then I have u equals e to the 2x, v equals x cubed. Okay, so u is the thing that's the composition. Okay, so if I do u prime, that's ln of the base, repeat the exponential. This is the outer function, the outer exponential function. And then take the derivative of the inner function, and that's the 2x in the exponent. Okay, so u prime, if I were to rewrite it, again, you'll see that ln of v is a 1, so that goes away. I have 2e to the 2x. Okay, everybody all right with it? I'm showing you all of this because I want you to see I'm reapplying the same pattern over and over again for differentiating an exponential. It's just when your base is e, things are a lot simpler. Okay. Now for v prime, that's easy. That's 3x squared. Okay, and then I have f prime of x. I'm just going to follow my pattern. Okay, so I have u prime, so 2e to the 2x times v plus u, which is e to the 2x, times v prime. Okay, so here's u prime, v prime. Okay, just so you can see the bits. If you want to simplify it a little, okay, you can probably pull out the exponential. So e to the 2x. Okay, and what will that leave behind? Okay, this would leave behind 2x cubed. Okay, from the first term. If I divide out the exponential, and it'll leave 3x squared back. Okay, I would simplify it like this, even though some of you were thinking, but wait, there's another common factor. I could pull out an x squared. Yes, but I would simplify it like this because if I need to differentiate it again, like to take its second derivative, I want it separated by type of function, exponential function times a cubic. Okay, if you pull out one of the polynomial factors as a common factor, you're going to destroy that. Okay, so again, keep it as exponential and not exponential. Okay, everybody see why I factored the result the way I did. See why I factored the result the way I did? Again, I'm giving you the opportunity to ask algebra questions. Okay. And this would be very easy to factor again if I wanted f double prime of x. Okay, again, it's a product of an exponential and a cubic. Just the cubic's a lot more complicated this time. Okay. All righty. I think probably everybody's running out of steam, so let's just do one more. Okay, number 12. Okay, find the equation of a tangent line to the curve y equals this expression at the point 0, -1. Okay, I need an equation of a tangent line. Okay, so what do I have to build the equation of a line? What do I need to build the equation of a line? Go all the way back to introductory algebra. What do you need? Slope and a y-intercept. Good. Okay, so think of your old friend y equals mx plus b. Okay, what we need is we need an m and we need a b. Okay, everybody good with that? Okay, how do I find the slope of a tangent line to y at 0, -1? Okay, how do I find a slope, the slope of a tangent line to that function at that point? Right, okay. So what you want to remember is slope of a tangent line to y at 0, -1 is y prime with x equals 0 substituted in. Okay, that's how I have to do it. Find the derivative, y prime, and then put in this x value. Remember, this is a point, so this is x, that's y. Okay, there's not going to be any y's in my derivative, so I'm just going to need to plug in my x. Okay, so let's do that. Okay, I would say if I were going to differentiate y, how would you find y prime? Okay, so again, just tell me in words, how would I find y prime? And I meant that's a single quote, not a double quote. Anybody want to give me any ideas? How would you differentiate this? What does it look like? Yeah, it looks like a quotient. Okay, and I don't see any easy way out of the quotient. Okay, so I need the quotient rule. Okay, so that's if y equals u over v, then y prime equals, and then just write the pattern down, v times u prime minus u times v prime over v squared. Okay, so there's my quotient rule. And again, my quotient rule may look a little different from yours, but it's the same idea. It's bottom function times derivative of top minus top times derivative of bottom all over the bottom function squared. Okay, it doesn't matter if you call them f's and g's or u's and v's. Okay, just make sure the pattern is correct. Okay, so u is my top function. V is my bottom function. These are straight quadratics, so they're easy to differentiate. This gives me a 2x, and this also gives me a 2x. All right, so if I put this into y prime, I'm going to get b times u prime minus u times b prime, the whole thing over b squared. Okay, but now I need to evaluate at x equals 0. Why? Because, well, this line, this tangent line, is going to go through this point. This is called the point of tangency. It's the point where your tangent line touches your curve. Okay, so we know that this point is on the line as well as being on the curve. So I'm going to plug in its x value, which is really easy. Thank goodness it's a 0. Okay, so this is 0 plus 1 times 2 times 0 minus 0 squared minus 1 times 2 times 0. And this is 0 squared plus 1 squared. And again, I think you can tell from looking at the numerator, this factor is 0, and it's multiplying this factor. So this whole first factor is 0, first term. This factor is 0, and it multiplies this, so this second factor is 0. My numerator is 0, my denominator is 1. So my slope is 0. Okay? And again, if you're not comfortable doing it by eyeball, just put it in your calculator, and you'll see that this numerator here becomes a 0. Okay, so now we've got y equals 0x plus b. Okay? How do I find b? Okay, so again, I should have typed it in here. How do I find b? What do I have to do to find b? Okay, you've got another piece of information here. Yeah, okay. Y is your b, exactly. So what you're going to do is you're going to take your pair, your ordered pair that's been given to you, which is y is negative 1, x is 0, not that it matters because your slope is 0. Okay, so here's your x, here's your y, and you get negative 1 equals b. So now your equation is y equals 0x minus 1, or y equals negative 1. Okay, so your tangent line to your curve is actually a horizontal line at y equals negative 1. Okay, don't think that your slope can never be 0. Of course it can. Okay, that's true when you've got a horizontal line. Okay, how are we doing? Okay, with number 12. Anybody questions on 12? All right. I'll just let you know that almost all of the rest of the problems in here are applied problems. Okay, so what we did so far was what I like to call math book problems. In other words, they're the type of problems nobody's ever going to ask you outside of a math class. And they strictly involve the basic skills and manipulations required to do calculus. Okay, the rest of the problems are more real life in the sense of they might be something you'd need to know. Okay, so some of them will be physics, some of them will be business problems. Okay, but that's what we're going to look at next time. So I'm coming back to the meeting and I'm asking questions on any of the basic derivative stuff. Questions on any of the basic derivative stuff?